enantiomers for a second here. Okay, here we go. So we're going to move on to section 5.5, where we are going to learn a new type of stereoisomer. So far, we started talking about isomers, right? And we talked about how there's constitutional isomers. These have different connectivity, and I gave you some examples of those during last class. And now we're talking about stereoisomers, right? That's the focus of chapter 5. Now, so far, we've talked about enantiomers, and we defined what enantiomers are. They're non-superimposable mirror images. The definition is right here. They differ the same way your left hand differs from your right hand. They're mirror images, but you can't put them on top of each other. You can't superimpose them, okay? We said, okay, well, if one enantiomer rotates plane polarized light in one direction, the other is going to rotate it in the opposite direction, the same amount, right? But now we're going to talk about what are called diastereomers. And diastereomers are non-superimposable. They have the same connectivity, but they're non-superimposable, and they're not mirror images. So to put it another way, enantiomers are stereoisomers that are mirror images, and diastereomers would be stereoisomers that are not mirror images of each other. I can show you right back to somewhere towards the beginning of this class and show you a very simple example of something that would fit the definition of a diastereomer. If you remember last class, we talked a little bit about these two molecules, cis and trans 2-butene, and I explained how there is no free rotation around a pi bond. I even showed you with my model that I would break it if I tried to, interconvert. There is no equilibrium between these two. It's impossible. There is no equilibrium between them. You actually have to break a bond. And so these are stereoisomers. Why? They have the same connectivity, don't they? They both go CH3, CH, double bond, CH, CH3. They both are connected in the same way. However, the arrangement of the atoms in space is different from each other, isn't it? And so since these are stereoisomers, but they're not mirror images, are they, right? If you look at a mirror plane here, you can clearly see they are not a reflection of one another. So by definition, they are diastereomers. Okay? Diastereomers, like enantiomers, will also have different physical properties. I mean, you just think about, diastereomers are going to have different physical properties. Enantiomers have the same physical properties. Anyhow, what I was thinking about was, if you think about the way that a bunch of molecules, let's say you had 1 mole, Avogadro's number, 6.02 times 10 to the 23rd power of cis-2-butene molecules, they're going to pack together differently than if you have 1 mole of trans-2-butene molecules. And therefore, they're going to have different boiling points, different melting points, different densities, different refractive indices, so on and so forth. So that's kind of your introduction to what a diastereomer is, right? Diastereomers are stereoisomers that aren't mirror images of each other. Well, we can take this even further and look at compounds that have chiral centers in them. Let's take a look at cyclohexane, a cyclohexane that has 3 substituents, okay? It's got a hydroxyl, it's got a methyl, and it's got a chlorine, okay? And here we go. So the hydroxyl is on carbon 1, the methyl's on 2, and the chlorine is going to be on number 3, like that. All right. Anyhow, so I've got 3 chiral centers in my molecule, don't I? I've got one here, I've got one here, and I've got one here. Well, I know that, and I'm just going to zoom in on this for a second. I know that if I have this molecule, and if I invert every wedge, if I convert them all to dashes, I'm going to have an enantiomer, aren't I? Right? When I flip everything, I've got an enantiomer. So if it's 1R, 2R, 3S, the enantiomer is going to be 1S, 2S, 3R, right? I flipped all the R's to S's and the S's to R's. Okay, those are enantiomers. And you can see that if I manipulate those stereocenters, that I can actually produce 4 sets of enantiomers. Okay, I'm not going to go over every single one of the molecules in here, but let's say you pick these 2 molecules down here, right? I have a wedge, a dash, and a wedge. Now I have a dash, a wedge, and a dash. All right, I have 1R, 2S, 3S. I flip all those. I get 1S, 2R, and 3R. So these are a pair of enantiomers. Again, repeating myself. In each one of these green rectangles, you have 2 pairs, or a pair, I should say, of enantiomers. But how many total stereoisomers do we have here, right? We have a total of 8, don't we? There are 8 total stereoisomers that are all drawn here. You can't have any more than that. Again, and I'm repeating myself for the third time, these are enantiomers, these are enantiomers, these are enantiomers, and these are enantiomers. Well, I want to broaden our definition of stereoisomers. What would be the relationship between this molecule, let's say, and this one? Right? What would be the relationship between those? Well, they have the same configuration at 2 of the chiral centers, but they differ at 1. So what's the definition? They're stereoisomers, right? They differ in the arrangement of their atoms in space, don't they? You can see that clearly by the chlorine. However, they are not enantiomers. They are not mirror images of one another. So therefore, they are diastereomers. So that means that this first compound that I have in the yellow circle, let me go backwards here, okay? This first compound is a diastereomer to this compound, this compound, this one, this one, this one, this one. They're all, so it means the first compound, this one right here that I'm putting the star by, has a total of 1, 2, 3, 4, 5, 6 diastereomers. Okay, it's only got 1 enantiomer, but it's got 6 diastereomers. We could do that for any of the compounds on this page. Okay, let's say I just chose one at random. I close my eyes and boop. Okay, there you go. I'll pick this one right here. It's got 1 enantiomer, right? But it's got 1, 2, 3, 4, 5, 6 diastereomers. Let's pick one of these at random. I'll erase some of the circles here. Okay, if I look at the relationship between these two right here, how do I know they're diastereomers? Well, if I look at the stereochemical configuration, you can see that it's the same at one of the chiral centers, isn't it? It's the same at this chiral center too, but it's different right here. Okay, therefore, they're not enantiomers, but they're stereoisomers, aren't they? The arrangement of atoms in space is different. Therefore, they are diastereomers. So you need to know the difference between an enantiomer and a diastereomer. And again, a diastereomer, and I'm just repeating it over and over and over, is a stereoisomer that is not an enantiomer. All right. Now, how could I predict the number of total stereoisomers I could have? Well, since we have 3 chiral centers, and this is going to be on another slide too, but since I have 1, 2, 3 chiral centers in my molecule, the way to predict a lot of the time, not 100% of the time, but the way to predict how many stereoisomers you could possibly have, or the maximum number of stereoisomers would be 2 to the power of n, where n is the number of chiral centers. Chiral centers. And again, it's on another slide, but I just want to go over it here. So if I have 3 chiral centers, 2 to the power of 3 is equal to 8. Okay, so that means the maximum number of stereoisomers I could have of this molecule is 8. And I do have 8 different stereoisomers. Let's look at a molecule that's even more complicated. Okay, so we're going to move on. And I know a lot of you, or some of you, I should say, are doing biology degrees. Okay, and you've probably heard of cholesterol, right? You know a little bit about cholesterol and some of its uses. Well, cholesterol is an alcohol, but cholesterol has a whole bunch of chiral centers. I'm not going to take the time to identify them, slowly here, but we have one here, 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 here. We have another one here. There's one here, and there's one here. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8 stereocenters. So if the maximum number of stereoisomers is 2 to the power of n, and I have an n equal to 8, then I have 2 to the power of 8. What's 2 to the power of 8? 2 times 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 2, which gives you 256 possible stereoisomers. Wowzers. That, my friend, is a lot of different stereoisomers that are possible of cholesterol. Of course, we're not going to write them all down, but what's kind of cool is that cholesterol will have what? It's got 1 enantiomer, right? And you could draw that out really quickly. All you'd have to do is draw the compound again. Everything it's a wedge, you make it a dash. Everything it's a dash, you make it a wedge. There you go. That's the enantiomer. So it's got 1 enantiomer, I should say, but it's going to have 254 diastereomers. 254 diastereomers. Okay. But nature only makes this one chiral compound. It only makes this one stereoisomer, cholesterol. And if you think about it, it's pretty remarkable that there's a total of 256 different stereoisomers that the body could make, but it only makes one. It's pretty cool, huh? Anyhow, let's take a look at some molecules and see if we can further cement our knowledge and our understanding of the difference between enantiomers and diastereomers. So that's all we're answering here. We're looking at these pairs of compounds and we just want to answer, are these two compounds here, for example, are these enantiomers or are they diastereomers? Could anybody answer A for me? Would I be dealing with enantiomers or diastereomers here in A? Yeah, in A, they're enantiomers, right? How do I know that they're enantiomers? Because I have two chiral centers in the molecule, this one here, okay, and then I have another one here. What did I do? This is a wedge, now it's flipped to a dash. This is a dash, now it's flipped to a wedge. So everything is perfectly inverted. Every stereocenter was inverted, and so these are enantiomers. If you want to look at it another way, and I think it's even more complex to do it this way, but if you were to take this molecule, let's say, okay, if you were to rotate this 180 degrees, what would you end up with? You'd end up with this. So let's draw it. You'd end up with this, and this methyl group here would now be pointing up if you did a pancake flip, and this methyl group would now be pointing down like that. You can see that this molecule and this molecule are mirror images of each other. And so either way, you can tell that these two compounds are enantiomers. So we'll write here, A is enantiomers. Okay. Again, what I think is the quickest way is just this one is flipped and this one is flipped. Therefore, everything's flipped, so they're enantiomers. What about B? What would those be? In B, I see somebody says they're diastereomers. I see other people agreeing. I think those people are right. How do you know that? Because one chiral center is flipped, whereas the other one is the same. It wasn't flipped. So that means that they are not enantiomers, right? If they were enantiomers, everything would be flipped. But we only have one chiral center flipped here. And so these would be diastereomers. Diastereomers. And then the last one is definitely the trickiest of all of them. And there's two ways to solve this one too, okay? One way would be to evaluate the chirality at the chiral centers. So you get, well, anyhow, I could highlight them all in different colors, but you've got a chiral center here, you've got one here, you've got one here, and you've got one here. You would just evaluate the chirality of all of these, right? So let me show you how to do that one first, okay? We'll start with the green chiral center. I'm going to move a little bit quickly just in the interest of time. This is my highest priority group. The hydrogen's in the back. This is my second. This is my third. It's going clockwise. Therefore, that stereocenter is R. So we'll put an R here. Okay. The one that I have highlighted in red, the chlorine is the highest priority. This is second. This is third. The hydrogen's in the back. That's going clockwise. Therefore, this is R. This one, make this smaller arrow. So we have R and R. Now we're going to compare the one in blue here. I have the hydroxyl, which is number 1. This is number 2. This is number 3. Therefore, that's R. Okay, so this one's R. And this next one here, okay, the one in yellow, I don't like to use the yellow pen a lot. I'll use black, okay? So I have the hydrogen going in the back here. Chlorine is number 1, this is number 2, and this is number 3. So it's going like this, which is counterclockwise. And so this stereocenter is S. Okay, so we have S. Now remember, you don't always have to look at dashes and wedges. Since this molecule is RR and this molecule is RS, yeah, you can see that one stereocenter was flipped. One remains the same. Therefore, these are diastereomers. Diastereomers. Now, if you don't want to go through all the labor of doing that, you could rotate one of the bonds, right? Because you see that this isn't exactly, in the same orientation. So what I would suggest, and this is, you could do it a bunch of different ways, but if we rotate this carbon-carbon bond to put this chlorine in the plane like this one, so I'll do that, and there's not a lot of room for me to do that, but after you rotate that, you end up with something that looks like this. You'd have the chlorine in the plane. You'd still have your hydroxyl up here, okay? But if the hydrogen is going in back, okay, and the chlorine is going in the plane, that means that the hydrogen would be coming out front and the methyl group would be going in the back, like that. So you can now see that this stereocenter is the same, but this one has been flipped. Now, I've taught this class long enough to know that in order to go from here to here, this is one of those times when handheld models come in really, 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 really handy, okay, while you're learning it. But you've got to be able to rotate bonds in your mind to some degree, okay? So, and if you have to draw every atom in and say, well, the hydrogen here is coming out like that, that's no problem, okay? So what's the best way to master this is practice. You know, I work with somebody in the chemistry department who obviously studied organic chemistry as a student and a graduate student. Then the person took a job where they got away from organic chemistry for a number of years. And then the person came back, you know, to organic chemistry again. You know, life has a, you know, John Lennon said, life is what happens while you're busy making plans. And anyhow, he came back to organic chemistry after, you know, he'd been away from it for maybe a decade or even more. And he told me that one of the things that he struggled with the most, you know, he said it's like riding a bicycle. A lot of it just came back to me. But he said the thing that I found the most difficult coming back was stereochemistry. You know, the whole concept of manipulating molecules in your brain. You know, it's not always an easy thing to do. So we'll do some more practice today. But let's move on to section 5.6, which deals with the consideration or considering rather symmetry in a molecule when we're looking at chirality. All right. By definition, if you have a compound, some kind of organic molecule, and it's got one chiral center, it's a chiral molecule. Okay. It's a chiral compound, done. Okay. But when you've got more than one chirality center, now wrap your head around this. Okay. If you haven't read the book, this will be like kind of a mind-blowing moment for you, maybe. If you've got more than one chiral center, okay, the compound might be chiral or not. Okay. You know, if you're thinking, well, how in the heck, Mr. Dion, could a compound have chiral centers and then the compound not be chiral? You just told me it's got chiral centers. How could it not be chiral? Because remember, the definition of something being chiral was what? Is that it was able to do what? It was able to rotate plane polarized light. So let me show you, and you're going to get it as soon as I show you the answer. Okay. If you take a look at these two compounds, we got cis and trans 1,2-dimethyl cyclohexane, right? They both have two chiral centers. There's one here, there's one here, there's one here and here. But notice that the title of this section is Symmetry in Chirality, right? If I was to ask you to draw these molecules in 2D, I'm sure you would all draw them faster than me. My Apple Pencil here, where you got, you know, the methyl coming up, you got a methyl going down. Over here, you've got a methyl coming up, you got another one coming up the way that it's written. But do you notice that one of these molecules has a plane of symmetry in it? Right? Is it the cis or the trans that has a plane of symmetry? And it's not a trick question. Mr. Dion does not like trick questions. Is it the cis or trans that has a plane of symmetry? Does anybody see the plane of symmetry? Yeah, absolutely. It's the cis that has a plane of symmetry in it, right? You can see it, you know, whether you're looking at the Haworth projection or if you're looking at, you know, this structure here. There's a plane of symmetry here, which is the same plane of symmetry there. So you can see that there's a beautiful plane of symmetry in the compound. Well, if I have, now wrap your head around this and check this out. Check out how cool this is. If you have a chiral center here and you have a plane of symmetry here, what does that mean? That means that chiral center is going to have the opposite configuration, isn't it? Right? These are mirror images. They're chiral centers, but they're mirror images. What happens when we have a 50-50 mixture of two enantiomers? They cancel each other out, don't they? So what it means is that, is this chiral center going to rotate plane polarized light? Hell yeah. Pardon my language. Yes, it will. Absolutely. Will this chiral center rotate plane polarized light? Absolutely. Okay. But what are they going to do? Since they're in the same compound, you always have a 50-50 mixture. They cancel each other out. And so that's how you can have a chiral center in a compound, yet the compound overall is not chiral by definition. Still has the chiral centers, but it's not chiral because it doesn't rotate plane polarized light. Give me a thumbs up if you just follow me on the idea, and we're going to talk about it even more. But just give me a thumbs up if you follow me on the whole idea of two chiral centers, but they're mirror images, in the same compound. Okay, cool. Yeah, it's kind of a cool thing when you think about it. I remember the first time I heard this, I was like, I never would have thought of that, but it makes sense. You know, if I guess if you have a mixture, a racemic mixture, yeah, they're going to cancel out. But if you have two chiral centers and they're just stuck inside the same molecule, and it's, you know, got a mirror, it's got a plane of symmetry, yeah, they should cancel each other out. Okay, so here's some more information about this. It says the trans isomer is chiral, but the cis isomer is not chiral. It's got chiral centers. Yes, it does. It's got two beautiful chiral centers. But overall, the molecule is achiral, right? Because it doesn't rotate plane polarized light because it's got that plane of symmetry. Okay, the cis isomer has a plane of symmetry. It is superimposable on its mirror image, right? If you were to flip this, either way, you see the exact same thing. And so therefore, you have kind of like two little enantiomers stuck inside the same compound, if you will. It's not the way we treat them. But molecules, they have an even number of chiral centers and have a plane of symmetry. They have a special SATSI name in organic chemistry. We call them Meso Compounds. So if we go all the way back here, you could say that this compound is a, oops, I don't want to write with a highlighter. There you go. We call this a Meso Compound. Okay, compound that's got chiral centers. Right, this is Meso. Okay, and yeah, so it's called a Meso Compound. Another way to test to see if a compound is meso, you can do this too, is just test to see if it's the same as its mirror image. So if you write out the mirror image, it's identical, well, you, my friend, have a meso compound. Okay, so you can practice by drawing out the cis and just showing that you could superimpose it on top. But by definition, when a compound is identical to its mirror image, it's not chiral, it's achiral, end of story, you know? So if a compound is a plane of symmetry, it is achiral. All right, that's just a definition in organic chemistry. So if we just zoom in on this compound right here, okay, this is a nice compound. It's trans, 1,2, a cyclohexane diol, good, great, yep, wonderful. It's got a chiral center here. It's got a chiral center here. Remember I told you the formula 2 to the power of n, where n is the number of stereo centers? So the maximum number of stereoisomers I could have here is 2 to the power of 2, which is 2 squared, which is 4. If I read out all 4 stereoisomers, remember I told you that this number represents the maximum. It doesn't represent the total, but it's the maximum that you could have. But what happens is, if you start messing around with all your dashes and wedges, what you find is that if you have 2 wedges like this, you have a plane of symmetry, right? You have a meso compound. So if you write it with 2 dashes like this, it's the same compound, isn't it, right? Think about it. If you were to draw a line here, and if you were to rotate this 180 degrees, you'd end up with this molecule. It'd be the same thing. Okay, so in this case, we actually only have 3 stereoisomers. Okay, so there's 3 stereoisomers, since 1 is a meso compound. And I don't know why the word meso isn't on here, but this is the meso. Right? And this is the same compound, so it's also meso. Anyhow, you get it. All right, well, let's move on from there and take a look over here. It says, draw all possible stereoisomers for each of the following compounds, and each possible stereoisomer should only be drawn once. So if we look at the total number of stereocenters that we have in the first compound, we have a stereocenter here, and we have a stereocenter here. So let's start by drawing it where we draw the 6-membered ring. And I'm going to start by drawing a wedge and a dash. So that means that one of the methyl groups is coming up, the one on the top, and the one on the bottom is going down. And now I'm going to draw its enantiomer. So I'll start with the 6-membered ring. I'm just going to flip the 2 stereocenters like that. Well, what if I had both of the methyl groups on the same side of the molecule, right? Then I'm going to draw my 6-membered ring again. I'll start with 2 wedges, okay, like this. And then what if I had them both pointing down? Well, let's draw that. Okay, now the question tells us that we should only draw each compound once. Does anybody see the problem here? There's a problem with my answer if I should draw each compound only once. Mr. Dion made a boo-boo here. Yeah, exactly. Exactly. Yes, one of the compounds is a meso compound, right? This compound here is meso. And so this is the same thing. So I can delete this compound. So I can, oops, maybe I'll just leave it there for instructional purposes, and I'll just cross it out. So I should have a total of 1, 2, 3 compounds, right? These two here, this one and this one, or maybe I'll just put it like this. These two are enantiomers. They're mirror images of one another. And then if I look at the relationship between, say, this one and this one, or this one and this one, those would be diastereomers, right? There you go. So maybe I could put another arrow. I don't know. I could just do like this. This one and this one and this one. Those would be diastereomers. Diastereomers. Yeah, exactly. Great. Great. I'm glad you guys are following along with me here. I don't think stereochemistry is an easy, I don't think it's an easy subject, you know. Again, here we have 2 chiral centers. So we would have 2 to the power of 2, right? N is the total number of stereocenters, so that equals 4 possible stereoisomers. But here we subtract 1 and we end up with 3 because one of them is a meso compound. So let me highlight the word meso so it really sticks out there. All right, let's give the next one a try. Hey, I'll just throw it out there to my students who I know are very quick. Could anybody tell me with this one here, how many stereoisomers I would have? And remember, this is a safe space. You know, just answer it to the best of your ability. All right. Oh, am I getting some answers here? Yeah, I got one answer. Getting a couple answers here. Well, let's double check, right? Because my students are seeing for sure that there are 2 stereocenters, right? There's one here and there's one here. So let me grab my red pen here. So if we have, right, 2 to the power of 2, that equals a total of 4. Well, let's start by doing this, and we'll put one hydroxyl going up, and then we'll draw the other one going down. Then we'll draw the mirror image. So we'll have one hydroxyl going down and one hydroxyl going up. So these 2 compounds are enantiomers. However, if I draw the compound so that I have both hydroxyls on the same side, like this, I do have 2 chiral centers, but I have a plane of symmetry down here. And so this is going to be a meso compound, right? If I was to write out, let's say I'll use blue here. If I was to write this, okay, that would be wrong because these 2 compounds are identical. Give me a thumbs up if that helps. And of course, this is something you're going to have to practice. You know, you have to look at it again. Everybody follow me on that? That there's only 3 in this case? Yeah, okay, cool. Because why? Because we have a meso compound. So we'll just cross this one out like that. So we have a total of 3 stereoisomers. There you go. All right, great. Meso compounds. You know, something about meso compounds that's interesting is it always surprises me whenever I'll be lecturing in organic chemistry too. And, you know, maybe let's say stereochemistry isn't something we've been talking about recently. You know, we're really into the nuts and bolts of synthesis, let's say, and I'll ask my students about a meso compound. It's one of those compounds that, or one of those compounds. It's one of those concepts that seems to stick. It seems to stick with students for some reason. You know, some concepts are harder to remember than others, but meso compounds is usually one that seems to stick with students. I can't answer why. I don't know, but it just does, which is a wonderful thing. It makes me really happy when something sticks with my students. All right. Well, I'm just looking at my notes here. Just give me a quick second here. See, what time is it?